What if the world's most heavily protected missile tunnels weren't ever defeated by bigger bombs, but by a completely different way of thinking? For decades, Iran invested enormous resources into building one of the most extensive underground military networks in the Middle East. Hidden beneath layers of rock, reinforced concrete, and carefully engineered infrastructure, these facilities were designed around a simple strategic assumption. If an adversary could not physically reach the launch systems, then those launch systems could survive almost any conventional air campaign. That assumption shaped years of military planning. Satellite imagery, official military footage, and public statements gradually revealed long tunnel systems, hardened entrances, underground storage halls, and protected launch positions. The message was always the same. Depth equals survival. The mountain itself becomes part of the defense. But modern warfare rarely rewards static assumptions. History repeatedly shows that every defensive breakthrough eventually creates an offensive response. The contest is rarely about building stronger walls. It is about finding entirely new ways to make those walls less useful. That is where the story becomes interesting, because the real competition may no longer be about penetrating mountains. It may be about understanding how those mountains actually behave. Before we continue, if you enjoy military strategy explained beyond the headlines as we break down the technology, logistics, and strategic thinking shaping modern conflict. Now let's begin. Underground military facilities are not unique to Iran. Throughout the Cold War, both NATO and the Soviet Union built hardened bunkers deep underground. China maintains extensive tunnel networks. North Korea has invested heavily in buried military infrastructure. The basic logic is straightforward. Depth complicates detection. Rock absorbs blast energy. Underground facilities are naturally protected against weather, observation, and many conventional attacks. Iran expanded this concept significantly over several decades. Rather than relying entirely on exposed launch sites, planners emphasized dispersed underground infrastructure connected by long internal corridors. Such designs can improve survivability by allowing equipment to move between protected locations while reducing exposure to surveillance. Engineers also incorporated redundant power systems, ventilation networks, reinforced access points, and multiple internal chambers. From an engineering perspective, these are impressive projects. Constructing large underground complexes inside hard rock requires sophisticated excavation techniques, extensive structural reinforcement, and years of continuous work. Every additional meter of rock increases the difficulty of any potential attack. Yet engineering always involves compromise. Every feature that increases protection may also introduce new operational challenges. A tunnel must breathe. Personnel require ventilation. Vehicles require movement corridors. Power systems require maintenance. Communication cables require protected routing. Emergency exits must exist. Every solution introduces another design trade-off. This is where military engineering becomes less about concrete and more about physics. Imagine speaking inside a narrow hallway. The sound reflects repeatedly between the walls. Inside a large open field, that same sound disperses almost immediately. Pressure behaves similarly. In confined spaces, energy does not always disappear as quickly as it does in open air. Instead, reflected pressure waves can interact with surrounding structures in complicated ways. Military researchers have studied these effects for decades because underground environments behave very differently from surface battlefields. The geometry of enclosed spaces can amplify certain physical effects while reducing others. Ventilation shafts may redirect pressure. Long corridors may channel blast waves. Multiple chambers can produce complex interactions that engineers attempt to predict long before construction begins. None of this means an underground complex automatically becomes vulnerable. In fact, properly designed facilities include numerous measures intended to reduce these risks. Blast doors, pressure relief systems, segmented compartments, shock isolation structures, emergency venting mechanisms. Modern military engineers understand these problems well. Likewise, military planners studying hardened targets understand them just as carefully. The competition becomes an engineering contest rather than simply an explosives contest. Instead of asking, how do we build a larger weapon? The question becomes, how does this entire underground system actually function? That represents a major shift in modern military thinking. Rather than viewing a tunnel as a single target, analysts increasingly study it as an integrated system. Power generation, ventilation, internal transportation, communications, structural geometry, access routes. Each component contributes to overall survivability. Each also creates dependencies. Modern intelligence collection reflects this broader perspective. High-resolution satellite imagery can reveal construction patterns. Thermal observations may indicate active ventilation. Repeated imagery collected over months or years helps analysts understand traffic flow and infrastructure changes. Open-minded source imagery combined with engineering knowledge allows researchers to build increasingly detailed assessments of underground facilities without ever entering them. This process relies less on dramatic discoveries and more on patient observation. One image rarely tells the full story. Hundreds of images collected over time often do. Military planners call this pattern of life analysis. Understanding how a facility normally operates may prove just as valuable as understanding where it is located. Once that picture becomes clearer, strategic options begin to expand. Not necessarily because the target becomes easier to destroy, but because planners gain a better understanding of which parts of the system matter most. Sometimes disrupting a critical support function produces greater operational effects than attempting to destroy the entire structure. That principle has shaped infrastructure targeting for decades. Airfields depend on runways. Ports depend on cranes. Communication networks depend on relay nodes. Underground facilities also rely on supporting systems that make daily operations possible. This is why modern military planning increasingly focuses on systems rather than individual buildings. The objective is often to reduce operational effectiveness instead of pursuing total physical destruction. And that distinction changes almost everything. The evolution of modern bunker-penetrating weapons reflects that broader philosophy. Popular discussion often focuses on bomb size. Military planners usually focus on something much more important: placement, timing, target characterization, and the sequence in which different capabilities are employed. Reaching a deeply buried facility is only one challenge. Understanding what lies beneath the surface is another. Modern intelligence networks combine satellite imagery, synthetic aperture radar, terrain analysis, electronic surveillance, and years of accumulated mapping to estimate how underground complexes are organized. Analysts look for construction spoil, ventilation patterns, support buildings, electrical infrastructure, transportation routes, and changes that occur over time. Each observation adds another layer to the operational picture. No single sensor tells the whole story. Instead, information from multiple sources is fused into a continuously updated assessment. Only then can planners begin evaluating which options are realistic. This illustrates an important change in modern warfare. Weapons are increasingly guided by information rather than simply by explosive power. A precision strike begins long before an aircraft takes off. It begins with intelligence. Engineers create detailed terrain models. Mission planners evaluate geological conditions. Rock density, tunnel orientation, structural reinforcement, and possible internal layouts all become part of the planning process. The weapon is only the final step. Everything before it determines whether that weapon can achieve its intended objective. Stealth platforms add another layer to this equation. Aircraft designed to reduce detection can approach defended airspace while limiting the amount of warning available to air-defense networks. That reduced warning time can compress an opponent's decision cycle, making it more difficult to reposition assets or activate contingency plans before a strike occurs. Again, the advantage is not simply the aircraft itself. It is how stealth, intelligence, electronic warfare, navigation, and mission planning operate together. Modern military operations increasingly rely on this integration. Every capability supports another. Every system becomes part of a much larger network. That same systems minus-based approach also changes how hardened underground facilities are evaluated. Instead of asking whether a mountain can be destroyed, planners may ask very different questions. Can access routes be interrupted? Can logistics be delayed? Can command and control functions be disrupted? Can maintenance become more difficult? Can operational tempo be reduced? Sometimes limiting a facility's ability to function creates greater long-term effects than attempting to eliminate the structure entirely. Military history offers many examples of this principle. Strategic infrastructure often loses effectiveness not because it is completely destroyed, but because the network supporting it becomes increasingly difficult to sustain. Underground missile facilities are no exception. Even heavily protected sites still depend on personnel, electricity, communications, transportation, maintenance, spare parts, and continuous coordination. The deeper and more sophisticated the facility becomes, the more complex those support requirements often become as well. That creates an enduring balance between protection and operational flexibility. Greater protection usually requires greater infrastructure. Greater infrastructure creates additional dependencies. Those dependencies become part of the broader strategic calculation. This is why modern military analysis places growing emphasis on resilience rather than invulnerability. No system is truly immune. The more relevant question is whether a system can continue performing its mission under sustained pressure. That distinction matters. A facility may remain physically intact while experiencing significant operational disruption. Conversely, a damaged facility may recover quickly if its supporting network remains functional. Success, therefore, cannot always be measured by visible destruction. Sometimes the most significant effects are invisible: delayed logistics, interrupted communications, reduced sortie generation, slower decision-making. These outcomes rarely produce dramatic headlines, yet they can influence military operations just as much as physical damage. The same logic applies beyond the battlefield. Underground missile infrastructure exists within a larger strategic environment. The Strait of Hormuz remains one of the world's most important maritime choke points, carrying a substantial share of global energy shipments. Any military development affecting regional deterrence naturally attracts international attention because the consequences extend well beyond the immediate participants. For both regional governments and outside powers, the objective is not simply military advantage. It is also maintaining strategic stability while preventing miscalculation. That makes credible deterrence especially important. A capability does not necessarily need to be used to influence behavior. Often, the demonstrated ability to hold critical military infrastructure at risk becomes part of the deterrence equation itself. Throughout history, advances in military technology have repeatedly shifted that balance. Fortifications once considered nearly impregnable eventually faced new engineering solutions. Battleships yielded to carrier aviation. Fixed-air defenses adapted to stealth aircraft. Electronic warfare evolved alongside precision-guided weapons. Each generation of technology forced military planners to rethink assumptions that had previously appeared permanent. Underground infrastructure is part of that continuing cycle. As defensive engineering advances, offensive planning evolves in response. Neither side remains static for long. Future underground facilities may incorporate more advanced compartmentalities, distributed layouts, autonomous monitoring systems, or improved pressure management technologies. Likewise, future intelligence, precision guidance, and systems analysis will almost certainly continue improving as well. The competition never truly ends. It simply changes form. Perhaps the most important lesson is that modern military superiority increasingly depends on integration rather than individual platforms. Success comes from connecting intelligence, surveillance, precision strike, cyber capabilities, logistics, electronic warfare, and strategic planning into a unified operational framework. No single aircraft wins that contest. No individual weapon wins it either. The advantage belongs to the side capable of combining many different capabilities into a coherent strategy. That is ultimately why discussions about underground missile complexes are not really discussions about concrete or geology. They are discussions about adaptation. Every military invests enormous resources to solve yesterday's problems. The challenge is anticipating tomorrow's. History repeatedly demonstrates that technological competition rarely produces permanent answers. It produces temporary advantages. Sooner or later, every breakthrough inspires a countermeasure. Every defensive innovation encourages offensive adaptation. Every new layer of protection creates another engineering puzzle waiting to be solved. That constant cycle has shaped military history for centuries. It will almost certainly continue shaping the future. The real strategic question, therefore, is not whether underground missile complexes can ever be made completely secure. It is whether military planners can adapt faster than their competitors. Because in modern warfare, the decisive advantage rarely belongs to the side with the largest weapon. It increasingly belongs to the side that understands the entire system better than anyone else. In the end, the contest is no longer defined solely by firepower. It is defined by information, by engineering, by logistics, by timing, and by the ability to connect every one of those elements into a single operational picture. That may be the most important lesson of all. Modern conflict is becoming less about overwhelming force and more about understanding complex systems. The battlefield is evolving from a contest of destruction into a contest of precision, integration, and decision-making. And in that environment, the side that learns faster often gains the greatest strategic advantage. If you enjoy this analysis, subscribe for more depth documentaries exploring the technology, strategy, and engineering behind today's most consequential military developments. Thanks for watching, and I'll see you in the next episode.